For nearly 100 million years after the Big Bang, the universe existed in complete cosmic night. There were no stars, no galaxies, no planets, not even dust. Only a vast, silent ocean of hydrogen, helium, and the faintest traces of lithium drifted through expanding space. Temperature slowly fell, matter spread out, and the cosmos waited, empty, dark, and nearly featureless. Astronomers call this epoch the Cosmic Dark Ages. It was a time when gravity had not yet gathered enough material to spark nuclear fire, when the universe was still too smooth, too young, too cold to shine. Every point of darkness we see in deep space images once stretched across the entire cosmos. And yet, hidden within this seemingly empty void, tiny fluctuations of density, left over from the earliest moments of existence, were beginning to deepen. Gravity tugged gas into invisible wells carved by dark matter. Slowly, silently, the first structures began to form. Then, at some point around the 100 million year mark, everything changed. When enough hydrogen collapsed under its own weight, pressure at the center ignited nuclear fusion. For the first time, the universe produced light. The birth of the first stars, what we call population 3, was the moment the cosmos ended its primordial night and entered its first true dawn. These were not stars like the sun. They were giants of pure hydrogen and helium, hotter, brighter, and more violent than anything alive today. Their appearance transformed the universe forever, turning a cold and silent darkness into a place capable of forming galaxies, planets, and eventually life. This is the story of that first cosmic sunrise. To understand why the first stars were unlike anything we see today, we must begin with a simple truth. The early universe had no metals. In astrophysics, metals mean every element heavier than helium, carbon, oxygen, nitrogen, iron, silicon, and all the building blocks that shape modern stars. None of these existed yet. They had to be created later inside stars. So the very first generation, population 3, formed from a primordial gas made almost entirely of hydrogen and helium, the purest in the universe's history. This absence changed everything. In today's cosmos, gas clouds cool efficiently because metals and dust radiate heat away. Cooling allows clouds to collapse into many small fragments, each forming a star roughly the size of the sun, sometimes larger, sometimes smaller. But in the early universe, primordial gas could not cool this way. Without metals, it remained warm, resisting collapse. Hydrogen molecules, H, were the only efficient coolant available, and even they were scarce. As a result, the gas could not break into many small, dense clumps the way it does now. Instead, it collapsed into fewer, far more massive fragments. These protostars grew enormous because nothing stopped them from gathering more material. Every collapse event tended to funnel matter into a single dominant core rather than distributing it into dozens of small ones. Simulations suggest that population 3 stars were likely tens, hundreds, or even thousands of times more massive than the sun, blazing hot and short-lived. The conditions required to create them were also extreme. The early universe was expanding rapidly. Gas was diffuse and needed strong gravitational wells, formed by dark matter, to compress it. Only in the deepest pockets of early cosmic structure could the first stars ignite. Thus, population 3 stars were not only giants, they were inevitable giants. Their size, temperature, color, and violent lifespans were direct consequences of the chemical poverty of the early cosmos. They were a different class of star, forged by a universe that had not yet learned how to make smaller, gentler suns. This is what makes them unique. They were born from a cosmos that had no past, no metals, and no memory, only gravity, gas, and silence. The birth of the first stars was not a gentle process. It unfolded in a universe that was still young, cooling, and overwhelmingly simple. Yet within that simplicity lay the seeds of the first cosmic structures. It began with the tiny density fluctuations imprinted on the cosmic microwave background, subtle ripples left behind by quantum variations stretched across space during inflation. In most places the gas was almost perfectly uniform, but in a few pockets it was just slightly denser. Gravity amplified those imperfections, pulling more and more matter inward. These ripples became the first gravitational wells. But visible matter alone was not enough to initiate collapse. The early universe needed a deeper scaffold, and that scaffold came from dark matter. Dark matter gathered first, forming invisible halos, regions of enhanced gravity that ordinary matter could fall into. Without dark matter's silent architecture, gas would have remained too diffused to ever coalesce into stars. Inside these halos, Clouds of hydrogen and helium began to cool, contract, and flow toward their centers. But cooling was slow, primitive. There were no metals, no dust grains to radiate away heat, only rare hydrogen molecules offering limited relief. As the gas compressed under its own weight, it heated until its thermal pressure pushed back against gravity. Only in the largest halos could gravity overcome this resistance. Eventually, deep inside these collapsing clouds, a protostar emerged, a dense, opaque core growing hotter with every passing moment. The higher the pressure, the more violently particles collided. As the temperature climbed into the millions of degrees, the primordial gas reached a threshold no star before had ever crossed. In this pure environment, devoid of carbon, oxygen, or any heavier element, the first thermonuclear reactions ignited. Hydrogen nuclei began to fuse directly into helium through the proton-up-proton chain, releasing light in a cosmos that had never known starlight. These reactions would have been far less efficient than modern stars, forcing population 3 stars to burn hotter and brighter in order to sustain themselves. Thus the first stars formed, not from the ashes of older generations, but from the untouched chemistry of the newborn universe. They were the first furnaces, the first beacons, the first architects of everything that would follow. If the first stars were the spark that ended the cosmic dark ages, then their physical nature was the fuel that ignited the early universe. Population 3 stars were unlike anything that exists today, giant, violent, short-lived titans, born in an environment so simple that it produced extremes rather than balance. Their most striking characteristic was mass. Modern stars form in metal-rich gas clouds that fragment easily, creating many smaller stars. But the primordial universe had no such cooling agents. Without carbon, oxygen, or dust grains to radiate heat away, collapsing gas clouds could only cool slowly, which meant they formed enormous protostars. Theoretical models predict typical masses of 30 to 300 solar masses, with some simulations allowing for even more monstrous giants, perhaps 500 or even 1,000 solar masses, before radiation pressure blew away the surrounding gas. Their surface temperatures were extreme. While our Sun glows at about 5,800 K, population 3 stars are believed to have burned at tens of thousands to millions of degrees, pushing their photospheres into the white-blue region of the spectrum. They were so hot that their radiation could ionize entire surrounding regions, creating enormous bubbles of plasma in the early cosmos. With such high temperatures came unimaginable luminosity. Population 3 stars were not merely bright, they were cosmic lighthouses, outshining present-day stars by orders of magnitude. A single one could rival small galaxies in ionizing output. Their intense ultraviolet radiation flooded the early universe, initiating the era of cosmic reionization. But perhaps the most defining trait was their chemical purity. These stars formed in a cosmos that contained no metals at all, no carbon, no nitrogen, no oxygen. As a result, their internal physics and radiation spectrum were fundamentally different. Without heavy elements to absorb or emit light, their spectra were almost featureless, dominated by hydrogen and helium transitions. This purity also meant their cores burned faster and more violently, because metals help regulate the flow of energy in modern stars. Population 3 stars lacked such stabilizers. This absence of metals made them inherently unstable. Their massive cores generated intense radiation pressure that pushed outward against their own gravity. Small disruptions could cause pulsations, rapid mass loss, or catastrophic instabilities. Their life cycles were brutally short, often just a few million years, compared to billions for most stars today. And in their deaths, they shaped everything that followed. Their extreme masses determined their fates. Some collapsed into the first black holes. Others detonated as pair-instability supernovae, blasting heavy elements into space. And some may have left behind no remnant at all. Population 3 stars were not gentle forges but roaring furnaces, reshaping the cosmos in a single brilliant outburst of existence. The first stars were born in silence, but they lived like storms. Their existence was a brief, incandescent flash against the backdrop of a dark young cosmos, a life measured not in billions of years, like the stars we know today, but in may tens of millions, sometimes only a few million. Their short lifespans were not a flaw of nature but a direct consequence of their immense size and primitive composition. Population 3 stars were extraordinarily massive, and mass is destiny. The greater a star's mass, the more fiercely gravity crushes its core, and the hotter that core becomes. For these titans, central temperatures climbed into unimaginable regimes, igniting thermonuclear fusion at rates our sun could never approach. With temperatures soaring into the millions of degrees, hydrogen burned at an accelerated pace, producing enormous amounts of energy in every second. This furious burning meant they consumed their fuel with reckless speed. While small stars sip hydrogen slowly, population 3 stars burned it like an open furnace in a vacuum, exhausting their primary fuel source long before they had the chance to settle into stable life cycles. Another factor sealed their fate. They were forged in a universe devoid of metals. Metals act as subtle regulators inside modern stars, helping to transport energy, absorb radiation, and balance the internal flow of heat. But the first stars had no such internal stabilizers. With only hydrogen and helium, their interiors were governed by raw thermal pressure and nuclear reactions alone. Their inability to efficiently shed excess energy made them hotter, more luminous, and significantly more unstable. As a result, their entire evolutionary sequence was dramatically accelerated. After a rapid formation and a short main sequence phase, they entered advanced burning stages at breathtaking speed. Helium fused into heavier elements, sometimes progressing all the way to oxygen and beyond. Their massive cores contracted and heated until they approached the limits of physical stability. In the end, their lives were not gentle fades but catastrophic endings. Some underwent pair instability, self-destructing in explosions so powerful they left no remnant behind. Others collapsed inward, forming the universe's first black holes, seeds that would eventually grow into the supermassive monsters anchoring galaxies. Their existence was fleeting, but their legacy eternal. These first stars lived fast, died violently, and in doing so, forged the foundations for everything that came afterward. When population 3 stars reached the end of their short, furious lives, the universe witnessed explosions unlike anything that exists today. Their deaths were as extreme as their births, uncompromising, violent, and transformative. These were the events that shattered the cosmic silence and seeded the darkness with the first heavy elements. The most massive of these primordial giants met their end in what physics calls pair instability supernovae. This rare and extraordinary mechanism occurs only in stars with enormous cores, where temperatures climb so high that photons, the very light that normally provides outward pressure, begin to convert into pairs of particles, electrons and positrons. This conversion robs the star of its internal support. The radiation pressure drops, gravity surges, and the core collapses catastrophically. But unlike ordinary core collapse supernovae, where the implosion rebounds into an explosion leaving behind a neutron star or black hole, the pair instability process triggers a runaway thermonuclear detonation. The entire star ignites at once. There is no collapse, no remnant, no core left to become a compact object. In a single titanic flash, the star destroys itself completely, unleashing an explosion up to 100 times more energetic than typical supernovae. These blasts were so bright that they could illuminate the deep cosmic night across millions of light years. They were the first great fireworks of the cosmos. More importantly, they were the first sources of heavy elements. Until this moment, the universe consisted almost entirely of hydrogen and helium. The extreme pressures inside population 3 stars forged carbon, oxygen, silicon, iron, and other elements essential for planets, atmospheres, oceans, and eventually life. When these stars detonated, they expelled their enriched interiors into surrounding space, polluting the pristine universe with cosmic metals for the first time. Those metals would become the seeds of the second generation of stars, population 2, and everything that followed. Not all population 3 stars were massive enough to undergo pair instability. Many collapsed in a different way. Their cores imploded under gravity and formed the first black holes. These early black holes became the gravitational anchors for future galaxies, growing rapidly by feeding on gas and merging with one another. Eventually, some of them would become the supermassive black holes we see at the centers of galaxies today. Thus, the deaths of population 3 stars were both symmetrical and paradoxical. The largest erased themselves completely. The smaller left behind the universe's first dark engines. In both cases, their final moments reshaped the cosmos, ending the primordial era and giving rise to the chemical and structural richness we see today. Their violent ends marked the beginning of everything complex. Inside the hearts of the first stars, the universe performed alchemy for the very first time. Until population 3 stars ignited, the cosmos was a chemically barren place, an ocean of hydrogen, helium, and a whisper of lithium. There were no planets, no metals, no dust grains, no molecules beyond the simplest forms. Everything complex, everything heavy, everything solid had yet to be born. The interiors of these colossal stars became the first crucibles of nuclear fusion, where unimaginable pressures and temperatures forged the raw elements that would build all future worlds. As hydrogen fused into helium at tremendous rates, the cores grew hotter and denser, allowing new reactions to unfold. Through the triple alpha process, helium nuclei fused to form carbon, marking the first appearance of one of the most essential elements in the cosmos. From there, the chain continued. Carbon fused with helium to produce oxygen, the element that would one day fill the atmospheres of planets and flow through the cells of living beings. Further fusion stages created neon, magnesium, and silicon, each step building heavier nuclei, each step deepening the chemical richness of the future universe. In the largest population 3 stars, nuclei combined until they formed elements as heavy as iron, the energetic boundary of stellar fusion. But these treasures could not remain locked inside their stellar furnaces. They needed a violent delivery system, and the deaths of population 3 stars provided exactly that. When these giants ended their lives in spectacular pair-instability supernovae, they tore themselves apart completely, scattering their newly forged elements across enormous regions of space. The shockwaves propelled carbon, oxygen, silicon, iron, and countless other nuclei into the surrounding medium, mixing them into the once primordial hydrogen and helium clouds. This cosmic enrichment is known as the metallization of gas, the transformation of the interstellar medium from purity to complexity. These metals acted as cooling agents, allowing gas clouds to fragment more efficiently. With improved cooling came smaller star-forming clumps, and thus the birth of population 2 stars, the next generation. For the first time, the universe could produce solar mass stars, planetary systems, and the chemical diversity needed for rocky worlds. In this way, the first stars did more than illuminate the early cosmos, they rewired its chemistry. They marked the beginning of the universe's long journey from simplicity to complexity, from hydrogen to life, from darkness to structure. Every atom of carbon in our cells, every grain of silicon in the Earth's crust, every molecule of oxygen that fills our lungs traces its lineage back to those first, ancient furnaces. They were the architects of the periodic table's first chapters, the forges that awakened the chemical evolution of the cosmos. The death of the most massive population 3 stars did more than end their brief, furious lives. It set the stage for the architecture of the entire universe. When primordial giants in the range of 150 to 300 solar masses exhausted their fuel, their cores collapsed inward with overwhelming force, creating the first black holes. These were not the supermassive monsters we see at galactic centers today. At first, they were only a few tens or hundreds of solar masses. Yet they carried within them a gravitational destiny far larger than their size. In the young universe, conditions were radically different from what we see today. Gas was denser, temperatures higher, and dark matter halos were rapidly growing. These early black holes sat inside those halos, where streams of pristine hydrogen and helium continued to fall inward. With so much fuel available and so little competition, they began to accrete matter at extraordinary rates, swallowing gas, dust, and even merging with other black holes. Some of them likely grew in sudden bursts, triggering bright accretion flares that lit up the primordial darkness. This process marked the birth of what astrophysicists call direct collapse black holes that skip the slow growth phases typical of modern stars and instead balloon rapidly into intermediate mass or even supermassive regimes. From initial masses of a few hundred suns, they could reach millions of solar masses within only a few 100 million years. These early black holes did not merely sit passively in their dark surroundings, they shaped the formation of the first galaxies. Their immense gravity anchored the growing halos of dark matter and gas, stabilizing the infall of material and helping the earliest proto-galaxies retain structure. As they accreted, they emitted intense radiation and sometimes launched powerful jets, heating the surrounding gas and regulating the rate at which stars could form nearby. This feedback acted like a cosmic thermostat. Too much heating, and star formation stalled. Too little, and gas collapsed too quickly, destabilizing the structure. In this delicate balance, the first galaxies emerged, small, irregular, chaotic systems surrounding a central gravitational well. Over time, mergers between proto-galaxies led to the growth of larger structures, and the seed black holes at their cores merged as well, gradually becoming the supermassive black holes that anchor spiral and elliptical galaxies today. Thus the population 3 stars, long vanished, left behind something far more enduring than their brief light. They supplied the universe with its first heavy elements, and through their collapse, they produced the gravitational engines that would eventually rule the cosmic landscape. Every large galaxy we know, including the Milky Way, likely traces its central black hole back to one of these primordial seeds. In this sense, the first stars did not merely illuminate the early cosmos, they engineered the blueprint of the modern universe. The first stars, population 3, remain the most elusive ghosts in the history of the cosmos. We know they must have existed, we can calculate the physics that governed their birth, and we can see the effects they left behind. But not a single one has ever been observed directly. They are simply too distant, too ancient, and far too short-lived. Their light faded more than 13 billion years ago, long before even the earliest galaxies fully settled into shape. Yet we are not searching blindly. Modern astrophysics gives us several powerful clues, footprints left behind by these vanished giants. One of the most important is the absence of metals in their spectra. Every star born after population 3 contains traces of heavier elements: carbon, oxygen, iron. Even the smallest fraction leaves unmistakable fingerprints in starlight. But a true population 3 star would show a spectrum of pure hydrogen and helium, untouched by any chemical enrichment. Telescopes like the James Webb Space Telescope scan the early universe for exactly such signatures: clean, metal-free spectra emerging from the cosmic dawn. Another pathway lies much closer to home, buried in our own galactic halo. The Milky Way contains ancient stars, survivors from billions of years ago, that formed soon after the death of population 3 giants. These stars have ultra-low metallicity, meaning they were built from gas enriched by only 1 or 2 primordial supernovae. By studying their chemical fingerprints, we can reconstruct the nature of the stars that came before them. Some of these ancient stellar fossils carry patterns so extreme, iron levels 1,000,000 times lower than the Sun, that they can only be explained by the explosions of the first generation of stars. We also search for the supernovae that population 3 stars would have produced. The most massive among them ended their lives as parent-stability supernovae, brilliant enough to outshine entire galaxies. JWST is now sensitive enough to detect the afterglow of such explosions across cosmic distances. A single detection of this rare signature would provide direct evidence for population 3 giants. And then there are the earliest galaxies themselves, tiny, fragile systems on the edge of the observable universe. JWST routinely pushes back the cosmic frontier, revealing galaxies formed just 300 to 400 million years after the Big Bang. Some of these show unusually blue colors and extremely low metal content, suggesting that their light may be dominated by the descendants of population 3 stars, or even their last remaining echoes. We stand today closer than humanity has ever been to identifying the first stars. The telescopes are powerful enough, the theory is refined enough, and the universe is finally revealing the first hints. It is only a matter of time before we glimpse the light that began it all. No population 3 stars survive today. Every one of them lived fast, burned violently, and vanished more than 13 billion years ago. Their lifespans were too short, their masses too extreme, and their environments too unstable to allow even a single survivor to reach the modern universe. The cosmic dawn was their era, and they left it long before the first galaxies grew to full size. But although none of these stars remain intact, their legacy fills the cosmos around us. Their first and most intimate descendants are the elements inside us. The carbon in every cell, the oxygen we breathe, the calcium in our bones, the iron in our blood, all of them trace their origin to the explosions of the earliest massive stars. Population 3 stars seeded the universe with the very first heavy elements. Without their supernovae, no later generations of stars, planets, or living worlds could have formed. In that sense, every person alive today carries within them the ashes of stars that lived before galaxies even existed. Their second descendants are the black holes that sit at the centers of galaxies. Many of the largest population 3 stars collapsed directly into black holes, forming the primordial seeds that later grew into the supermassive black holes we see today. These ancient remnants influence the structure, evolution, and fate of galaxies themselves. Every quasar, every active galactic nucleus, every titanic gravitational engine at the heart of a galaxy may represent the final echo of a star from the cosmic dawn. And finally, the third descendants of population 3 stars are the first galactic structures themselves. Their radiation shaped the early intergalactic medium, ionized the primordial gas and triggered the formation of the first galaxies. Their supernovae enriched collapsing clouds with metals, allowing the universe to transition from a dark, simple world of hydrogen and helium into a chemically diverse cosmos capable of forming planets, oceans, and life. So while no population 3 star shines today, their fingerprints are everywhere, in our bodies, in the hearts of galaxies, and in the architecture of the cosmos. Their light is gone, but their influence endures in every star born after them, and in every world that followed. The first generation of stars, population 3, reshaped the universe so profoundly that every cosmic structure we see today carries their imprint. Before they existed, the cosmos was chemically simple, a vast, cold expanse composed almost entirely of hydrogen and helium. There were no planets, no worlds with solid surfaces, no complex chemistry capable of supporting life. The emergence of population 3 stars marked the moment when the universe began to evolve beyond this primordial simplicity. Their greatest contribution lies in establishing the chemical history of the cosmos. Through their enormous masses and violent thermonuclear reactions, these stars forged the first heavy elements: carbon, oxygen, silicon, iron, the fundamental building blocks of planets, atmospheres, oceans, and biological molecules. Each population 3 supernova acted like a cosmic alchemist, enriching the surrounding medium with new elements and redefining what future stars could become. Without this enrichment, subsequent generations of stars would have remained metal-free, unable to cool efficiently, and incapable of forming stable planetary systems. Population 3 stars also prepared the universe for the existence of life. Every living organism is built from elements synthesized in earlier stars, and the very chemistry that enables life, from water molecules to DNA, requires heavy elements absent in the early cosmos. The first stars transformed a sterile universe into one with the potential for biology. Their explosions seeded future star-forming regions with the ingredients necessary for complex worlds to emerge. Finally, population 3 stars prevented the universe from remaining a dark, monotonous expanse. By emitting intense ultraviolet radiation, they initiated the epoch of reionization, altering the transparency of the intergalactic medium and enabling light to travel freely across vast distances. They jump-started the process of cosmic structure formation, influenced the growth of early galaxies, and shaped the thermal evolution of the universe. In essence, population 3 stars acted as the universe's first architects, forging its chemical diversity, illuminating its earliest epochs, and laying the groundwork for every star, planet, and living being that would ever follow. They no longer exist, but their influence defines everything that does. The story of population 3 stars is, in many ways, the story of the universe learning to shine. For nearly 100 million years after the Big Bang, the cosmos remained in perfect darkness, a vast, silent ocean of hydrogen and helium with no structures, no light, and no warmth. Then, from within this formless expanse, gravity pulled matter into the first dense pockets, and the earliest stars ignited. Their birth marked a turning point so profound that the universe itself changed character. Darkness ended. Structure began. Time, in the sense of cosmic evolution, truly started moving forward. These primordial stars no longer exist, yet their presence permeates everything we see. They forged the chemical seeds from which galaxies would grow. Their violent deaths enriched the interstellar medium with the first heavy elements, allowing new generations of stars to burn more gently, more stably, and with far greater diversity. Without their contributions, there would be no rocky planets, no atmospheres, no oceans, and no biochemistry capable of producing life. Every galaxy carries their legacy. Every star with planets, every molecular cloud, every element heavier than helium whispers of the explosions that ended their brief, violent lives. Even the iron in human blood and the calcium in our bones trace their origins to nuclear reactions that took place in those ancient giants. Population 3 stars did not survive into the present era, yet their fingerprints shaped the cosmos at every scale. They were the universe's first poets of light, illuminating the emptiness with brilliance that has echoed across billions of years. Their radiance re-ionized the early intergalactic medium, making the cosmos transparent and allowing the great architecture of galaxies to emerge. Their influence is not a memory but a foundation, woven into the chemistry of worlds and the physics of everything that followed. And so the poetic truth remains: we are the children of the first stars that flared into being amidst the cosmic void. Their light is gone, but their story continues in us, in every atom of our bodies, and in every corner of the night sky that still glows with the echoes of their dawn.